Hey physicists, we're in our waves unit and we're talking about light now. We've talked about reflection, refraction, and diffraction. So remember that reflection is the bouncing of a wave off a barrier. Refraction is the bending of a wave when it goes into a new medium. And diffraction is the bending of a wave when it goes around a barrier. So today we want to focus on refraction. So remember that's the bending as it enters a new medium. You can see an example on the back here where I have a beam of light shining into water and then it looks like it gets bent instead of following this straight line down. Same thing here, you have these waves coming this way and then they get bent to go in whenever they go in the water. You may have seen this sometimes if you're in a restaurant and the lighting is just right. Your straw looks like it is broken and it's not going the right way whenever it's in the water. That's an example of refraction. So the question then becomes, why does that happen? This bending is caused because the change in the wave's velocity and wavelength. So as it goes into the new medium, the frequency doesn't change, only the velocity and the wavelength changes. So remember that the speed of light is 2.99 times 10 to the 8th. We'll often round that to 3 times 10 to the 8th. But even light will go slower whenever it enters a newer, denser medium. So this is the speed of light in a vacuum. It's not the speed of light like through air or through water or through the atmosphere or glass or anything that the light can shine through. So why then does it go slower? And if you think through molecularly, that light is traveling from, if we go back to chemistry, whenever the electron gets excited, it jumps out to the next orbital or the next level, and then as it goes back into the orbital, it releases a light wave. So the reason it goes slower is not because the light itself isn't traveling slower, it's because the light comes in, it hits that first element, the first electron, jumps the electron out, and then the electron in essence like catches the light wave. Then it rethrows the light wave whenever it jumps back into the next orbital to the next atom. That electron catches it, rethrows it, catches it, rethrows it. And it's not the fact that the light is traveling slower, it's the idea that each atom is catching and throwing the light waves as it's going through the material. And that's what's causing it to slow down, is that catching and releasing of those light waves. So between the atoms, the light is still traveling at that 3 times 10 to the 8th. But whenever we talk about atom to atom, it's getting slowed down because of that. Now, when we do this, we can come up with a fraction that is, what is the regular speed of light, that 3 times 10 to the 8th, to the new velocity in that specific medium. So you'll see that that n value is going to be what we call the index of refraction. And then here's some common values for the n. We would say in a vacuum, that ratio has to be 1 because the speed of light is 3 times 10 to the 8th. And if I divide it by 3 times 10 to the 8th, I'm just going to get 1. Notice how really, really close air is to that. It's not quite the same, but very, very close. And then as we get water, the index gets higher, glass gets higher, plexiglass gets higher, a diamond gets higher. So you notice the density of the material plays into that, because the more dense it is, the more of that catching and throwing you're going to have. So what would be the speed of light traveling through plexiglass? Really basic problem here. We know that the speed of light, the C value, is the 3 times 10 to the 8th. We know that the plexiglass index of refraction is 1.51. And so we're going to just plug in those values and solve. So we could cross multiply and divide, or we could take our 3 times 10 to the 8th divided by the 1.51. And then notice that the velocity of light in plexiglass is 1.99 times 10 to the 8th. So it goes down fairly significantly, that 1.5 value for the ratio. So Willibrord Snell was he was a Dutch astronomer, mathematician. He actually wasn't in the early 17, it would have been the 1700s, which was the late 1500s, early 1600s, or the 17th century, when he discovered that this idea that whenever the light comes in, that it gets bent like that because of the fact that the frequency is staying the same. So when a wave enters a new medium, it slows down. And what that slowing down will do is it will bend the wave or bend the light towards the normal if it's going into a more dense medium. So when it goes into a more dense medium, it slows down, causing the light to get bent towards that angle or towards that normal value. When it enters a less dense medium, it will speed up and bend away from the normal. So that would be like if it were coming the other way, we're coming out of the glass and into the air. So notice that we have this normal. Remember that normal, again, is the idea that it is a perpendicular. Same thing we talked about when we talked about friction. It's the normal force which is the perpendicular force. And so we have this perpendicular line here, and the angle is always in reference to the perpendicular. So I have my angle of incident, or the incoming angle, and my angle of refraction, or the outgoing angle, whenever it's going into that. Well, what Willibred Snell came up with was this idea of what we call Snell's law, and he said that the angle, that the index of refraction of the incoming wave times the sine of the angle of the incoming wave is equal to the index of refraction of the refracted wave times the sine of the refracted wave. Or in essence, we end up with those two ratios of the indexes of refraction and of the sine values for that. And that was what Snell's law was. Again, a Dutch astronomer mathematician. So now let's do a sample problem on that. A light wave of 589 nanometers traveling through the air strikes a smooth, flat slab of crown glass that has an index of refraction of 1.52 at an angle of 30 degrees to the normal. So find the index of refraction, which would be the theta value. So super easy. We're given three givens on that. We have a wavelength, we have an index of refraction, and we have an angle. So we want to find a new angle for that. We also have that it is I guess we're going to say it's coming through air. So we also know that that index of refraction is the 1.003 that we showed on that earlier one. And so what we would do normally in our class, 9 out of 10 times, we're going to round that to just be 1. And so here are our given values. And once I plug that into my Snell's law, I end up with the index that it came from, so the 1 and the angle it came from, and I have the refracted value 1.52, and I'm solving for this refracted theta value. And when I do that, I'm going to inverse sine, divide those and inverse sine those, and I get an index of refraction of 19.2 degrees. So what we could do then is there's a really cool PhET simulation that we could double check this out on. So if I go to the PhET simulation there, so I'm looking at the PhET simulation here. It looks like I had it already up. I'm going to go to More Tools, and from More Tools, I can set this to be the I think it was 589 that was coming in at an angle of 30 degrees. So I'm going to set my protractor on here, move this up to be 30 degrees, and then I'm going to set this to be the crown glass that we said was 1.52, I believe it was. So let's look back at that. It was 1.52, yep. And notice then that that looks like it is really almost exactly on the 19.2 that we talked about. And so that's one way that you can play with that also, just to get with a simulation that you can play with to see that refraction. So again, Snell's law, this ratio of the index and the sine and the index of the sine, setting those equal to, and just solving for whichever one you don't know. And that is refraction.